Welcome to the Crazy Hat Chemist. So another video in kinetics. Let's see how fast we can go now. Bam! So today we're deriving the rate law and the rate constant, problem number 2. Okay, so we're going to derive the rate law and the K for the following reaction. That's NO plus Cl2 yields NOCl. Now this isn't balanced and that doesn't really matter because we really don't care about that. Okay, so the above reaction was studied at 23 degrees Celsius and the following data was collected. So I have experiments 1, 2, and 3. I have concentration in moles per liter, that's molarity of nitrogen monoxide, that's NO. And then I have concentration in moles per liter, that's molarity of chlorine gas, that's Cl2. Then I have the initial rate in moles per liter minutes of what the rate is. Okay, so I got 3 experiments here, and I need to derive the rate law. So we actually already know the basics of what the rate law is. The rate law is R is equal to K, that is the rate constant, times the concentration of the reactants. What we're really trying to solve for is the reaction order for both of the reactants. So we already have that skeleton of what the rate law should equal, and this is that skeleton. So R, that's the rate for the rate law, is equal to K, that's the constant, then the NO to the power of X. So we're going to solve for X here to determine the order of NO. And then the Cl2, and that's to the power of Y, and we're going to solve for the Y, and that is also the reaction order of the Cl2. So we need to solve for X and Y, then we'll have the rate equation, and then we can use the experimental data to determine the value of the rate constant. Very simple here. Okay, so we're going to find a set of 2 reactions in which one reactant is changing and the other reactant is held constant. So on the previous example, there was only one reactant, so it was very easy. This time there are 2 reactants. Okay, so the easiest thing to do is if we have the ability to look at 2 experiments in which one of the reactants is being held constant. That way we can look at the second reactant independently of the other one. Otherwise, we're going to have to juggle those 2 reactants up in the air at the same time and determine the rate of those, and that's a very complicated matter. So if we don't have to do that, it's much easier. Okay, so we're going to look at experiment 1 and 2, and with experiment 1 and 2, you should see that the NO is being held constant at 0.1 for both experiment 1 and experiment 2. So we're going to cross those out. So those are being held constant. So that means that the rate, the initial rate, is independent of the NO because that concentration is being held constant. So we're going to look at the Cl2 concentration and the initial rate and compare those two. And the Cl2 concentration is going from 0.1 to 0.2. Then the rate is going from 0.18 to 0.36. I want you to figure out the 0.1 to 0.2, hopefully that you know what that is. That's a doubling. And then the 0.18 to the 0.36, what is that? Well, that's a quadrupling. Sorry, a doubling as well. Okay, so we got a doubling of the concentration of the Cl and a doubling of the rate. So therefore, what is the order of the Cl? Okay, the order of the Cl is doubling of the concentration, doubling of the rate. That will be first order, and that's why there is a 1 for first order. All right, so now let's take a look at another set of reactions here, or experiments, and get the order of the NO and solve for the X. So we're going to look at reactions or experiment number 2 and 3. With experiment 2 and 3, you should see that the Cl at 0.2 is being held constant for both reaction 2 and reaction 3. So we're going to delete this out and it's being held constant. Therefore, the initial rate is dependent only on the NO and independent of the Cl2. All right, so we're going to look at reactions 2 and 3, and we're going to look at the concentration of the NO. It's going from a 0.1 to a 0.2. That is a doubling. Then we're going to look at the 0.36 and the 1.45, and that is a quadrupling. So if you double the concentration and you quadruple the rate, then what is the order of that reaction, and that is second order. Okay, so now we discovered these orders of both reactants. So now we're going to substitute that information in to write out what the rate law is. The rate law is R for rate law is equal to K, that's the constant, NO to the power of 2, and Cl2 to the power of 1. The overall rate for this reaction is a third order. Okay, that is 2 plus the 1. So the overall order is third order. Okay, now what we're going to do is we're going to derive the value of the K, that's the rate constant. Now you can use any of the experiments, experiments 1, 2, or 3, but I'm going to use the data for experiment 1, no particular reason, just I think you're number 1. Okay, so here is the data from number 1 plugged into that rate law. The R, that's the rate, okay, and that's 0.18 moles per liter minutes is equal to K. I'm solving for K, and the NO concentration for experiment 1 is 0.1 moles per liter, and that's going to be squared. Don't forget about that squared term. And then the concentration of the Cl2 is 0.10 moles per liter, and that's to the first power. So now I'm going to rearrange this, solving for K, solving for the numeric value, and solving for the units of it as well. Again, like on the previous video, you can solve for the numeric value independently and then solve for the units independently of each other, or you can do them simultaneously, whichever one works best for you. If it gets complicated again, remember to do them separate. Numeric value and then units in two separate things. But this is what you should get. The value for K is 180 liters squared per mole squared minutes. Okay, and that is the value for K. That's the rate constant. Okay, you can use this rate constant for and then determine the rate if you change for any NOCl2 concentrations that you want to plug into this rate law. You can now get the rate of it without actually doing another experiment. That is if you are using this at the same temperature, because remember the value of K is dependent on the temperature. All right, that was another awesome video here in Kinetics, and we're going to look forward to the next video in Kinetics. And here's a crazy hat, and I'm all turkey. Give me a thumbs up if you like that video, subscribe to my YouTube channel, and I'm going to see you next time for more cool chemistry videos. Until then, bye now.